Hi, and welcome to another discussion on thunderstorms. We're working our way through the hazards associated with thunderstorms, and in this particular video we'll cover lightning. So what lightning is, generally, it's an electrical discharge, of course, that tries to equalize separate areas in a thunderstorm that have distinctly different charge. And in order for this charge to occur, a couple of things need to happen. Number one, the cloud needs to go up through the freezing level, in other words, 0 degrees Celsius, and usually a good amount above the freezing level, anywhere from minus 10 to minus 20 degrees Celsius. It needs to at least reach up to those altitudes. And then finally, there needs to be a precipitation process occurring in the cloud. So the droplets need to get large enough, get above the freezing level, start to freeze, and then start to fall. And this is where Graupel comes in to help with the charge separation. Graupel is a snowflake that rhymes. You know what rime is, little droplets freezing on contact and causing a very low density type of ice. So you get a low density type of ice particle that's falling through a cloud. And as it falls through the cloud, ice crystals in the cloud are hitting or striking the Graupel particles as they fall. And as they do that, they give the Graupel a negative charge, and they take the positive charge and carry that up to the cloud in the smaller ice crystals. So because of this freezing process, the thermoelectric effect that occurs, the charge separation, the bigger particles get the negative charge and the smaller little ice crystals float up to the top of the cloud and take the positive charge. So that's what happens. The big ones get the negative, and the smaller ones get the positive. Smaller ones go to the top of the cloud, bigger ones go to the bottom. And as a result, you get this separation in cloud of mostly positive lightning or positive charge at the top of the cloud, including the anvil and portions above minus 20. And below that, you have mostly negative charge. So what happens with lightning is that there's a breakdown in the electric field. In other words, the electric field becomes so strong that the air can't act as an insulator and separate the two charges. So eventually there is some charge that seeps from one part of the cloud to the other. You have an equalization of charge. So that's what lightning is in a nutshell. And with lightning, the type of lightning that you get, whether it hits the ground or stays in cloud, is determined by the freezing level. With lower freezing levels, a lot of this charge separation is happening close to the ground, and as a result, the lightning strikes do occur to hit the ground. And this is very common in locations that have colder or colder temperatures. So in other words, you'll see this north of 30 degrees or 40 degrees latitude, and also in the southern hemisphere also. But in the tropics, what happens is, since the freezing level is so high, the lightning strike can't make it down to the ground, and it tends to equalize the charge in cloud. So those are more in-cloud lightning strikes. And then there's also cloud-to-cloud lightning strikes, and those are very rare. You don't see that very often, where two separate thunderstorms are connected by a lightning strike. So the way that lightning works is that first there's an invisible ionized channel of air that starts to seek its way to the ground if you're looking at a cloud-to-ground lightning strike. And usually this is very faintly visible. The visibility is caused by the electrons moving through the air and charging the gas molecules. But then it starts branching out, looking for the path of least resistance, and those electrons are flowing down. And this is a very low charge. Typically, the current is only about 100 amps. But then when the negative charge reaches a place where as it approaches the ground, a positive charge starts to rise up from the ground in any pointed object. So taller objects tend to get this positive charge to reach up and meet the step leader coming down. When that happens, the circuit is closed, and that means that electrons can start flowing. So what you see is a visible lightning strike because of the very fast flowing current, very high current that connects these two different areas. So this is the visible part of the lightning stroke, and it looks like it stretches up from the ground to the cloud, and the reason for that is because the circuit is made first at the ground or close to the ground. It's completed, and that's where the electrons start flowing quickly, and then as you move up higher, it taps into more and more charge. So the return stroke is, of course, the visible flash, and it's very high current, typically 20,000 amps for a cloud-to-ground strike. But if it's just an in-cloud strike, in-cloud strikes tend to be rather weak, and that's only 2,000 amps. 2,000 amps is nothing to sneeze at, but it is pretty intense. But still, it's less than what a cloud-to-ground lightning strike would be. Of course, as the current flows, the air heats up to a temperature of 50,000 degrees Fahrenheit. That rapid rise in temperature causes a pressure wave of about 10,000 millibars, and that's what we hear, that wave moving away from the lightning, what we hear as thunder. So that's the basics of lightning. Now, airplanes get struck by lightning by two processes. One, either they're at the wrong place at the wrong time, or the aircraft itself may trigger lightning. So being at the wrong place at the wrong time means that the aircraft is flying through an electric field, and a lightning strike or step leader starts to head from one charged area to another, perhaps from the cloud to the ground, or in cloud if you're flying through the cloud. And the aircraft just happens to be at the wrong place at the wrong time, and it ends up being part of the step leader. And that's what these figures show. This is from a NASA document. It shows that the aircraft is just in the wrong place at the wrong time, and if the airplane is charged, it'll send out an ionized channel of air also to meet the step leader, and it becomes part of the charge, or part of the circuit. So there are videos out there that you can watch showing cloud-to-ground lightning strikes where the aircraft just happens to be at the wrong place at the wrong time. Here's one of the links that you can look at. And there are two ways that this happens. Either an aircraft can break down the electric field, or it can become so charged that it creates a rapid electrical discharge. The first one we're going to talk about is the breakdown of electric field, and this is where an airplane is flying through the cloud. And as it flies through the cloud, it's flying through an electric field, and the exhaust plume from the jet is very warm. Of course, combustion is a very high temperature. When that happens, it ionizes the air in the exhaust, so it carries a charge, either positive or negative, and that acts as sort of like a conductor that will break down the electric field and allow ions to flow from one part of the cloud to the other, but then fly up the plume and then cause a tail strike on the aircraft. And this is seen quite frequently. You end up getting a lot of tail strikes, and they theorize that these tail strikes are because of the aircraft breaking down the electric field. The other way that an aircraft can trigger lightning is by picking up a large amount of charge. So what happens is, as the aircraft flies through a cloud. The cloud may be charged. Either it carries the hydrometeors carry a positive or negative charge, and it's not necessarily just hydrometeors. Even if you fly through sand or dust or volcanic ash, a lot of times these particles carry a charge. Pilots flying through volcanic ash have reported seeing glowing as a result of the charge that the aircraft picks up. So as the aircraft flies through the cloud, these particles strike the aircraft and then bounce off and then transfer their charge to the airplane. So the airplane picks up either a negative or a positive charge. And then as it flies or continues to fly through the cloud or the volcanic ash, it continues to pick up the charge. And the charge can be so great that weird things start happening to the aircraft. Actually, airplanes are designed to dissipate this charge. They put static wicks on the airplane, and static wicks are designed to get rid of this charge as the aircraft picks up the charge. But there are times when either the static wicks are broken and the airplane can't get rid of the charge, or there is so much charge in the atmosphere that it's being picked up. The airplane is picking up the charge faster than it can get rid of it. And as a result, the airplane will try and discharge in a couple of different ways. One way it does that is by actually kind of slowly discharging from pointed objects on the airplane. And that is what is St. Elmo's fire. St. Elmo's fire is a glow around the airplane at pointed objects, whether it be propeller tips, the nose of the airplane, wing tips, or the tail. You start to see a glow. And that's where the charge is leaving and exciting the molecules of air to the point where the air starts to glow. This is also seen on the, you can see a lot of videos at YouTube where they show actual kind of lightning, not really lightning, but just static electricity that's discharging. So it'll look like little shocks that are moving across the windscreen or other places. That is what is St. Elmo's fire. Sometimes, though, if the aircraft picks up the charge so fast and can't get rid of it quickly, you'll have a rapid discharge, an aircraft discharge, and that is aircraft-induced lightning. So you hear a boom, you see a flash of light, but typically the dissipation, the current that was transferred was usually pretty low. So you end up not having really any problems, just you're usually kind of disoriented and kind of shocked by the thunder and the lightning that you see. So as far as where airplanes get struck and how often, a little bit of climatology, it's frequent actually. Aircraft typically get struck once every 3,000 hours, and an airplane typically flies 3,000 hours a year. So most aircraft are getting struck once a year. And the locations where they get struck typically occurs, of course, in cloud and in rain, and usually around thunderstorms, but not always during cruise. Most times it's during takeoffs and landings, and climbouts, actually. And then here is the location, and this is very important to understand lightning. Remember that the positive charges are at the top of the cloud and negative charges are at the bottom. So it looks like at very high altitudes in the anvil, temperatures of -40, altitudes of 12 kilometers, which is 36 or 38,000 feet. That's where you see a lot of the minor flashes. And remember, minor flashes are in cloud. In cloud doesn't have a lot of current. But down low, where the airplane ends up being part of the cloud to ground lightning strike, cloud to ground lightning strikes are a lot stronger, and those are initiated near the freezing level. Remember, you need a freezing process to get charge separation started. So down low, you get a lot of major flashes, and that's where you start to see damage to the airplane, right around the freezing level. So what happens to the airplane when it gets struck by lightning? Does it explode? No, that is very rare. Typically, aircraft that have exploded were very low on fuel, so there is a mixture of air and fuel, vaporized fuel, in the tanks when the aircraft was struck. Here's one accident investigation from an aircraft, a Boeing 747 that flew into Madrid back in 1976 and was struck by lightning, and that did explode. But there have only been about 3 or 4 different cases that airplanes have exploded, and airplanes are getting struck by lightning every day. Typically, JP4 tends to be more volatile. And then other things that can happen, we talked about flame out. When you get struck by lightning up the tail, then that'll disrupt the flow of air around the engine and cause a compressor stall, and the airplane or the engine will flame out. This is more of a problem with airplanes that have fuselage mounted engines. And then typically lightning enters and exits at the most pointed object on the airplane. So that would be the nose and the tail, or the wingtips, or the empennage, meaning the horizontal stabilizer or the vertical stabilizer. Of course, objects that are non-metallic will tend to vaporize. Objects that are metallic will tend to melt. And then engines, typically turbine engines, if they get struck by lightning, there isn't a problem, but except for the Pratt & Whitney PT6, since it is a geared engine, the gearbox will be magnetized and it'll wear a lot faster. So it's a mandatory teardown if you're flying a turboprop aircraft. Here is a University of North Dakota King Air that was struck by lightning back in the 1990s, and here's some of the damage. And you can see that the propeller was melted, and then where the access door meets the fuselage, there is a little burn mark. The nose, the radome was, you can see a burn mark, and then on the ventral fin, you can see where it exited the aircraft and it was melted. This is an RJ, I think this is Air Wisconsin. A friend sent this to me and just shows objects that are not metallic tend to degrade pretty quickly. They burn and they will delaminate. So these pictures are a winglet on a wing, and you can see that's probably where either the lightning came through or left the aircraft. You can see the winglet is made mostly of composite, so it burns the metal pieces such as the screws. And there's a close-up, you can see some of the damage. Other problems involve avionics. If there is a strong lightning strike, that lightning may enter the circuit of the aircraft circuit itself, and may damage the avionics, whether it be analog or digital. And then other things, such as the magnetic compass may be magnetized, permanently magnetized, so you might have to swing the compass and take the aircraft out of service. If the lightning strike occurs at night, the lightning is so bright that may cause temporary blindness, so you can't see while you're flying at night. And then finally, if you're picking up precipitation static, in other words, if you're picking up a lot of charge on the aircraft and can't dissipate it, then you'll have problems with communications and also with navigation, meaning that the antennas will be charged and will not be able to receive or transmit any kind of electromagnetic radiation. Typically, it's a problem at low to medium frequencies. A lot of times people use ADFs as strike finders because they point to where the lightning is. So that's an overview of lightning.